Well, hello and welcome back to another episode. It's great to see you all. I hope you're doing well. So today we're continuing with our series on writing a ray tracer in C++ using as far as possible only the standard libraries and the SDL2 library so that we can display results in a window. This particular episode today I want to focus on UV projection. We'll cover what that is and how it differs to UV mapping that we've talked about before, and then we'll go on to look at how we can modify our code to actually implement that. Now that does require a fair amount of modification from the code that we have before, which is something that is unfortunately unavoidable. I've tried to avoid refactoring the code too much as we've been going along, but we do need to make a fairly substantial change to the code base today. But once we've done that, it opens the door for a great deal more flexibility and more features, so I think it's worth it. Anyway, hopefully that will be of interest. So just before we jump into that, I want to say, as I always do, that if you like this video, please do remember to hit that like button, and if you haven't done so already, please consider subscribing to my channel so that you don't have to miss any future videos. Thank you very much. Right, well, without much further ado, let's jump into it and let's have a look at UV projection. Okay, so first off, this is the image that we're going to be producing today. By the end of this episode, we will be able to render this. It's worth noting that actually most of the features that are demonstrated here in this image already exist within the public version of QB-Ray, which is available on the GitHub repository. So we already have capability for fuzzy reflections, as you see here. We already have the capabilities for normal mapping. As you see here, these embedded or indented, engraved letters, if you like, on the wooden blocks here. That's done using normal maps. Really, the new features that we're talking about today, particularly UV projection, is what we've used to apply the texture and the normal map to the cubes, to the cylinder, and also to more complex shapes such as the torus or donut shape here. So this is what we're going to end up with at the end of today's episode. So hopefully that will be of interest. Stick around if you want to see how to do that. To start with, I really just want to talk about a little bit about what UV projection is and how it differs from UV mapping. So we've already talked about UV mapping, and we've looked at how we can use that technique to apply textures to, for example, a sphere, as you see here, or indeed to a cylinder, as you see here. Now this is done using simple spherical or cylindrical projection directly onto those shapes. But what if we wanted to apply a UV map to a more complex shape? So in the case of simple shapes such as the sphere or the cylinder, we can quite easily calculate the coordinates or transform the point of intersection into the coordinates in the UV space. But with more complex shapes, that's really not so easy. So to illustrate one good thing about the system that we've put together in terms of this, let's consider the letter A in the QB-Ray logo more closely. Now, all of the objects in the QB-Ray system are defined in their own local coordinate system. So first of all, we have a global coordinate system shown here by the red, green and blue arrows. And then, as I say, every object has its own local coordinate system. And what we do is we actually define objects around their local origin, and then we translate, rotate, and scale them into the position that we want them to be in the scene. And this gives us many advantages. For a start, it allows us to quite easily make more complex shapes and objects and things like that, as we've already seen in previous episodes. And it presents an enormous advantage when it comes to trying to do a technique such as UV projection. So if we consider what happens when a ray from the camera strikes the letter A. So we see here in green, this arrow indicates or represents a ray from the camera. Technically it's from a point slightly below the camera, of course, so that we can see what's going on, but nevertheless it's representative. And we see that that ray strikes some point on the letter A. Now what we actually do when we test for intersections with objects, we don't directly use this ray with every object in the scene. What we do is we transform this ray into the local coordinate system of every object, and then we test for intersections with that. So what would this ray look like in the local coordinate system for the letter A? Well, it would look like the ray that you see here, the arrow representing the transformed ray here shown in purple, which you can see strikes the A in a local position as indicated. As we move the green ray left and right across the letter A, we can see how the purple ray also moves. Okay, so the green ray is in the global coordinate system from the camera to the object. The purple ray is the same as the green ray, except that it's been transformed into the local coordinate system for the letter A, and the letter A, of course, is defined about its own local origin. Okay, so if we focus just on the letter A, we can see that any local point of intersection is going to exist within that particular local volume. Okay, however we transform the A or any other object, the local coordinate system always stays the same. And that's really important, because what that means is that the point of intersection in the local coordinate space or system for the object will always remain the same regardless of how that object is transformed in the scene. And what that means is we can use that local coordinate, which I'm going to call UVW, to separate it, differentiate from the XYZ global coordinate space. We can use that to calculate a point that we can then use to calculate a texture or a color from a texture, or to do normal mapping or anything else. Now, in the case of normal two-dimensional textures and normal maps, then we transform that in some way from the UVW space to the two-dimensional UV space. But we could equally talk about volumetric textures as well, which is not something that I'm intending to go into at this point. Right, so I mean, we've already covered the basic mathematics of how we do UV mapping for spheres and cylinders and planes. That's in the previous episode. Very quickly to recap what we have. For a spherical UV mapping, we start with something like this. We have a sphere defined about its local coordinate system, so it's defined at the origin there, I've called it XYZ space here, that doesn't matter too much. If we consider a point of intersection somewhere on that sphere, then we can see that we can describe that point in spherical coordinates, U, V and R, as I've called them here. So U represents the angle around the orange circle that you can see here, V the angle around the yellow circle that you see here, and R is the radius, which we assume is fixed at 1. And therefore you can see that actually any position on the sphere, we calculate its coordinates in UVR, and we can disregard R, and then that gives us a two-dimensional coordinate UV that then represents a unique point on that sphere, which we can then use to define our position within the texture space. So we know the XYZ location, and all we need to do is actually convert those to spherical coordinates, which we can do using this equation here, these two equations here, sorry. So pretty straightforward, okay? For a cylinder, really very much the same. We have a cylinder defined about our origin, and then simply we can express any position there by the angle theta, the radius r, and the dimension z. So pretty straightforward. We already know the x, y, z, so to convert into cylindrical coordinates, we simply take the arctangent of y over x, and we set v is equal to z. So u is the arctangent of y over x, and v is equal to z. Note that in practice we use the a tan 2 function, not a cos 2 as I've written there, because tan to the minus 1 so the a tan 2 function will automatically handle the various edge cases. Okay, so that was a really quick recap of the basic mathematics behind sphere and cylindrical projection. Planar projection is pretty obvious. Projecting onto a box, like in the example image we saw at the beginning, is a bit more complicated, so we're going to come back and talk about that later. But I just want to show some examples. If we consider this example here, we're starting with a solid sphere, and if we make that sphere partially transparent, inside that sphere you'll see as a box. Now I want to show how we can use spherical projection to compute UV coordinates for a shape such as this box. As I mentioned, we will look at proper box mapping later, but just for this example, let's assume that we want to use spherical UV projection to project a texture onto the box. So for any point of intersection on the box, we can imagine, we're not constructing a ray, okay, but we can imagine a line that comes out from the origin of the box and passes through that point of intersection. Now, if we consider that line to be passing out to some imaginary sphere, the partially transparent sphere that you can see here, then actually we can calculate, using the equations that we've just talked about, any position u and v on the surface of that sphere. And that is indeed how we do spherical projection. And you can see what happens as we move the point of intersection around the box. You see how it moves around the sphere. And this plane here on the left shows the UV space flattened out. And you can see the green sphere on that plane moves about with our point of intersection to show exactly which part of the texture that we're looking at every point. And you can see that as the point of intersection moves around the box, the corresponding line moves around the sphere, and you can see how the corresponding point moves around the plane as well. Okay, that is the basic principles of spherical UV projection, we could replace the box with any shape we like, as we will see in a moment. Now, for cylindrical projection, very much the same. We start imagining a cylinder, as you see here, around our shape. If we make the cylinder transparent so we can see, we're doing exactly the same thing. We're casting a ray out, but not exactly from the origin. In the case of cylindrical projection, we match the z-coordinate, the vertical coordinate of the position, but otherwise we then cast it out into a circle around that point. And you can see then that how we get the same sort of effect. So you can see as we move the point of intersection around, you can see how that maps to different places in the cylinder, and how that therefore maps to different places on the plane that you see here on the left. Okay, so what if we had a more complicated shape, so something like a torus, such as we see here? Now this is quite an interesting case. So we can use spherical projection to map a texture onto the torus, as you see. So this is the example we have. And as before, I'm not showing the imaginary sphere in this case, but we are using spherical projection. And as you can see, as the point of intersection moves around the torus, you can see how that corresponds to the point in the UV space and the plane on the left. Now, of course, the torus is something of an interesting case. So for a start, the problem of using spherical projection with a shape such as this is that not every point on the surface will map to a unique point in the UV space. So if we zoom in on what's happening on the inside here, you can see that both the outside face and the inside face of the torus are going to map to the same point in the UV space. Now that, depending on what kind of texture you're doing, that isn't necessarily a problem. It could be an issue, or it might not. It just depends on your particular application. In the case of a torus, we can actually quite easily define a unique UV position, or UV coordinate, sorry, for every position on the surface. As you can see here, we can imagine a line out from the origin of the torus out to the center of the torus, and then a line from that point out to the edge of the torus, and we can rotate those separately. So we could consider the angle around the origin to be u, for example, and the angle around the center of the torus to be v. And you can see we could go all around the shape. We could define any point on that surface uniquely if we wanted to. So there's no particular reason that we have to use UV projection for a torus, except that perhaps it's just a little bit easier. So you might be wondering, what actually is the point of UV projection? Well, it comes into its own when we have shapes that we cannot define a unique point on the surface easily. Okay, so if we consider a shape such as this here, this is a sort of, I don't know what it is really. Well, it's a mixture of a cube and a sphere. I know exactly what it is, but I'm not sure what to call it. But anyway, it's a complex surface, okay? So with a complex surface like this, it would be very complicated to calculate the UV projection on its own. But where we can do the UV mapping directly, I mean. But if we use the UV projection technique, so here we're using spherical projection again, we can see how the point of intersection, as the point of intersection moves around the blob, well, I've called it a blob, around the complex shape, we can see how that maps to a unique point in the UV space and the plane on the left. And this works even for more complicated shapes that may have holes in them, such as this example here. And again, we move our point of intersection around the shape, we can see how the spherical projection maps that point to a point on the UV space shown on the plane on the left. Okay, so we can see it's a very powerful technique. It does have some limitations, but it is a very powerful technique that allows us to apply texture to virtually anything, really, bearing in mind the certain caveats that we have just looked at. Okay, so I mentioned at the beginning that the box mapping is a little bit more complicated, and actually it is. Now, we can use spherical or indeed cylindrical mapping to map a texture to a box, but that does result in a fair degree of distortion, as we saw in the examples now. And actually, there's a much better way that we can do it. If we consider starting with our texture mapped onto a plane, as you see here, if you think about how a cube is constructed, we would cut out a portion of that plane. You could see in this animation shows how we could fold that portion of the plane to make a cube shape. Okay, and this is the basis of how we can do cube projection, cube UV projection. Because all we need to do is, for every particular surface or face of the cube, we just need to map that to the corresponding location in the UV plane and then just treat it as we would normally for planar projection separately for each face. So you can see from this animation here that how the different sections of the total UV image map to individual faces of our cube. And in fact, actually, we can see that if we were to divide the UV space into a 4x4 grid, we can see that 6 of those 16 squares map to unique faces on our cube. And actually, although there's a bit of wastage there, you can see quite easily how you could therefore create a flattened image that therefore maps onto a cube. And this is the technique that we're going to use. So what we're going to do, when we come to look at the code, we will look more closely at exactly how we go about implementing that for the cube mapping or box mapping for the UV projection. Otherwise, that's it really for the theory. Now, I mentioned at the beginning that we would have to do some quite substantial refactoring to our code to implement this, and unfortunately we do. I've perhaps been a little bit lazy with writing the code so far, in particular with how we return information when we have an intersection between a ray and an object, or a hit between a ray and an object. And what I've done is simply define a bunch of variables that we return results into, and that's fine, it works, but it makes it very difficult if you later on want to add something extra to that. You have to go through and change every instance of that. So what I've done is define a data structure instead, and yes, I've had to change every instance where we return information from a ray hit, but at least now the data structure is defined. This isn't something that we'll ever have to do again, so I think it's worth covering it and going over it in some detail right now. So the very essence, really, of making UV projection work is that we need to be able to access the UVW coordinates of the point of intersection, so the point of intersection in the local coordinate system for every object. And so we need to return that information whenever we have a ray hit. And this is what I wanted to add to the return variables, and it's what prompted me to make this change. So this is the root folder that we have for our project. It's got a number of textures and things here, which I will include in the repository there to render the sample image that we saw at the beginning. If we go into the QB ray trace subdirectory and have a look at here we have qbutils.cpp and qbutils.hpp. So that's the first place that we want to have a look at what changes we've made. Okay, so in qbutils.hpp, I have defined our data structure called hit data. Okay, so in order to make this work, we have to refer to the object-based class, and we have to forward declare that, because this header file will be encountered before the compiler encounters the definition for object-based. So we simply forward declare that, and then it gets filled in later when the compiler comes to the proper definition for object-based. I've talked about forward declaring before. It's a standard C++ thing. So within a namespace called data, so we have qbrt and then a subnamespace for data, and we declare our structure called hit data, which contains the following elements. So the point of intersection, the normal at the point of intersection, the local color, and the new one is the local point of intersection, which is in the UVW coordinates. And then we also have UV coords, which is a two-dimensional vector, which is the actual coordinates of the UV space going in the UV space, which will be computed using one of the projection methods that we're going to talk about. And we also return a pointer to the object itself. Now that can be very useful, because if we want to interrogate that object for something else, or whatever we might want to do with it, that can just be useful to have. Okay, so print vector, this was something that we had in here before already. qbutils.cpp, no change there, that's just the code for print vector. Okay, so the first place that we look where we actually made some changes is in object-based.hpp. So this is the base class from which all of our object classes are defined. And what we do, we have a few things here that we have added. So first off, we defined these constants for the UV mapping types. Okay, so we use the const expression of type int, and we call these UV sphere, UV plane, UV cylinder, and UV box, and we simply map those to 0, 1, 2, and 3 respectively. Okay, so that's just really for convenience. It means wherever you want to use one of these, you can just do qbrt from the namespace : UV plane, for example. You don't need to remember that it's 1. Okay, so that's just for convenience, really. Now we have a function here to compute UV. We'll come back to that. And we have defined a public member variable of m_UV map type, which defaults to qbrt::UV sphere. Okay, right. And I think that's everything there. The last thing that's changed here is, of course, our test intersection. So every instance of the object class, every object that we implement has to implement a test intersection method or function, the purpose of which is to take the provided ray and test whether that ray intersects with that object. And what we've done, this is the first place you can see where I've made this change. So whereas before we passed as input the ray and then we returned an output separately for intersection point, local normal and local color, what we now do is return an instance of qbrt::data: hit data. So the hit data structure that we just talked about, called hit data, we just simply pass a reference to that so that we can return it. Okay, that is everything we need to do in objectbase.hpp. So in objectbase.cpp, again, we change our definition for the test intersection method. So I've commented out the original code here just to make it clearer what I've actually done. In all the other places that we go on to look at this where I've made this change, I won't do that. But just for this case, just so that you can see what's changed. Of course, this is the base class. It just returns false, okay, because that's going to be overridden in every instance. And then here we have our function to actually perform the UV mapping. Okay, so this accepts as input the local point of intersection in the UVW space, as I called it, and it returns the output called UV chords. Okay, so the first thing, we simply use a case statement based on m_UV map type, and this could be UV sphere, UV plane, UV cylinder, or UV box. And for each particular case, we simply do the necessary calculations. So for UV sphere, we extract our x, y, and z. This is the local coordinates, just from local POI, and then we do the calculation using atan2 and that for u and v exactly as we saw, and then we modify UV chords and then we finish. Okay, very straightforward. UV plane, even easier. We simply keep those as they are. Okay, cylinder, again, using the maths that we just saw, so that's really straightforward, exactly the same thing. Now, box projection, as I mentioned, is a little bit different. We extract x, y, and z, and we define u and v. And now what we need to do is identify which face of the cube that we're actually dealing with, okay? And we also define a UV transform matrix, which we initially set to identity. So we're using the close enough function to test whether, if the value of x is close enough to -1, we can't test for equality with -1 because we're using double precision floating points, then it's very unlikely that it will ever be exactly equal to -1. So what we do is simply take a figure that's close enough, okay? So if the x coordinate from our local POI is close enough to -1, then we assume that's the left face, okay? And if it's close enough to 1, +1, we assume it's the right face, and so on for the other faces. I think you can see what's going on there. And then in each one, what we do is we calculate u and v using this system. So the first thing we have to realize is that each square of our UV space that we're mapping to a face on the cube represents 1/4 of the total UV space in U and 1/4 in V, okay, because it's a 4x4, essentially divided into a 4x4 grid, okay. So the first thing we do is we multiply, in the case of the left face, we multiply y and z by 1/4, by 0.25, okay, which effectively scales the UV space up so that only 1/4 of it fits in that space between -1 and 1. And then in the case of y, we subtract -0.75, which is simply a shift in the u-axis, okay, as you can see there. And we don't need to do that for z because the left face lies along the origin. And then we basically do the same thing for the right face, front face, back face, top face, and bottom face. And that will give us our box. Now, a limitation is, with this method, that if we're not close enough to any face, then presumably the user is not trying to use the box mapping method to apply the texture to a box. They're applying it to something else. Now, that's a perfectly valid thing to do, but in order to implement that would require doing a bit more maths to calculate what the equivalent position would be, and that is something that I haven't done yet, and something we'll probably cover in a future video. So at the moment, the box projection method works perfectly if you apply it to exactly a box, but it will not work if you try to use box projection for another shape. So if you think about what we talked about with spherical projection, we can use that to apply the UV texture to any shape that we want, but we can't do that using the box projection method, at least at the moment. Okay, and then we simply return u and v as before. Okay, and we at the moment are not applying any transform to that. That is not implemented yet, something we can look at in a future video. Okay, so that is the code in the base class for our objects that actually calculates the uv coordinates given any local position. You can see how that's going to be a lot more useful than the system we had before. So previously, in any shape that we implemented, we would have to do the work to calculate the uv coordinates specifically for that shape, whereas now it's in the base class, it's already there, we don't need to worry about it. We only need to specify whether we want spherical, planar, cylindrical or box projection. Okay, so that's pretty powerful. Right, so the next thing to talk about is everywhere else where I've had to make modifications. I'll go through this quite quickly. If you look on the GitHub repository, you know, it's all there. And if you look at the Git log specifically, all of the changes I've made are described there. So you should be able to see quite easily. So in material base, this is the header file for material base. Now here we have a cast ray function, so this is one thing that has to be changed in that we've now modified it so that it uses the hit data structure to return the results of the cast ray. Okay, I think, yeah, and that is the only change to materialbase.hpp. Let's have a look at materialbase.cpp. Okay, so materialbase.cpp, we need to find the definition for cast ray. Here it is. So this is the cast ray function. This casts a ray into the scene and now uses the hit data structure. So previously we defined variables for intersection point, local normal and local color. Now instead of doing that, we now define an instance of our hit data structure. And for every object in the object list, we call the test intersection method using the ray that's been cast and we pass hit data. Okay, if we have a valid intersection, then we calculate the distance and we calculate whether it's the closest object. If it is, then we set closest object equal to current object and closest hit data equal to the hit data that we got back from the test intersection method. Okay, we'll have a look at specific implementations of test intersection in a moment. Okay, and that's it. That's really the big change there to material base. Now the other place where we have a cast ray function is of course in the scene class, so we have to modify the header file as before, but I'm just going to show the CPP file here for brevity. So in the CPP file we have below our render function that actually does the rendering, we have a cast ray function here. This is slightly different to the version that we've just seen, so it accepts as input a ray, a reference to the closest object, and of course it will return an instance of the hit data structure. Okay, so we start out now by defining that instance of the data structure, and we call the test intersection method on all of our objects passing hit data so that we can get the information back. And then exactly as we just saw in material base, we use or set the information in hit data accordingly. Okay, so we're setting the data in closest hit data to what we get back from hit data here. Okay, so that is the modification that we have to make there, or all of the modifications you have to make to those base classes. Okay. All the other places we have to make changes, we have to change our point light instance, so pointlight.cpp. Okay, this needs to be changed because it, where are we? Which bit do we have to change? Here we are, because it's calling the test intersection method on all of the objects in order to test if that object is casting a shadow for this particular light source. So here I've commented out the original code that we had, and this is the code that we have now. So we're now using the hit data structure that we define here, whereas previously we had defined POI, POI normal, and POI color. Okay, so that's the change that we need to make there. Yep, okay. Now also in the instances of the different materials, so simple material that inherits from the material base class, but we do have to make a change here because it is calling the different functions. So let's have a look. Yeah, so compute specular. So in the compute specular function, again, we have a call to the test intersection function for every object because we have to test if there's an object between the light source and us. So we're doing that. We're now returning hit data. Of course, in that case, we don't need to use hit data for anything, so that's pretty straightforward. That's easy. Okay, and that is everything there. And similarly, in the simple refractive class that implements a refractive material that we can use for glass or something like that, we make a very similar change here. So in compute translucency, because we're now casting another ray, we have to call test intersections, which we need to do here, and we're now using the hit data structure exactly as before. Okay, And yeah, I think that's everything. And this also uses cast ray, okay, from the material base class here and here, okay, which I've now modified also to use the hit data structure, okay. Okay, and as well there. Okay, so those are fairly straightforward changes. I don't want to talk about them too much. If you look through the code, then I think that's all going to make sense. And this implements compute specular as well, so that is also the same as what we just looked at. Okay. Okay, so that is everything for the lights and the materials. The last thing to look at is how we've made modifications to the actual primitive shape classes. So starting with box.hpp, we've modified, because this uses test intersection, it overrides the test intersection method from the base class. So we now put in reference to our hit data structure and override, of course, rather than what we had before. And let's just have a look at box.cpp. So box.cpp, we've updated the test intersection method, so it now uses the hit data structure, and everything else is the same to actually calculate the point of intersection. I haven't changed anything there. The only thing that's different is right down here at the end, where we now return the point of intersection in hitData.py, we return the normal into hitData.normal, we return the color into hitData.color, we return the UV coordinates. Now notice we're using the compute UV function, okay, which is what we just talked about. That's implemented in the base class, the object base class, and that will automatically work with whatever projection method that the user has specified, and we simply pass into that the point of intersection that we get from the code above, and pass m_UV coords, which is the variable into which it will put the result, and then we simply return that as hitData.UV coords, and there we go, and we return a pointer to the object. So we're using the C++ this keyword to get a pointer to the current object, and we use star this because we don't want the pointer, we don't want to return a pointer to the pointer, that would be silly. We want to return a pointer to the object itself, so we use star this. That means that we actually get the value that, or we get the thing that the pointer is pointing to rather than the pointer itself, and you make a shared pointer out of that of type object base, which we return into hitData.hitObject, and that is it. Basically all we have to do now is go through all of the different shapes and we do the same thing. So for example, cone.hpp, we modify the HPP file definition here for test intersection, and then in cone.cpp we simply modify it exactly as we've seen before, hit data, and then down at the end we have our code. There's two separate stages here because the cone has an end cap, but we're doing exactly the same thing, and we're returning the UV coords, the local point of intersection, and so on in the UV coordinates in the hit data structure, sorry. Okay, so all we have to do then is simply go through every primitive shape and do exactly the same thing. And I just want to show, I'm not going to show each individual one, but just to show how we do that for ray marching as well. So this is the ray march base class, so the base class for all of our ray marched objects. We simply modify the test intersection function as before to now use the hit data structure. In raymarchbase.cpp, again, we simply modify that. We do all the code that we had before to calculate the ray marching. One thing that is different now that you'll notice in this comment here is that I put in extra code to calculate an offset position. Now, this is an interesting thing about ray marching, that actually if you want to calculate the gradient of the sign distance function in order to get the surface normal, it is actually better to do that from a slightly displaced position rather than the point of intersection itself. So effectively we backtrack along the ray a very small amount, 0.01, to get the normal location, and then we calculate the surface normal based on that. Now the reason to do that is because where you have very complex objects which might have tight corners, you could, if you use the actual point of intersection, quite easily get a normal vector that points into the shape rather than out of it, which would obviously cause all sorts of problems, so that would be no good. So we do that, and then otherwise all we're doing is we're simply returning local POI and the UV coordinates and everything else exactly as we've talked about for all of the other shapes. Okay, so if we go back to the capp.h file for our ray tracer, then at the moment that's set up to render the scene I saw at the beginning. What I'm going to do is just comment that out. We'll put that in. So this will give us the test scene that we've used before. And if I go to my terminal window, I'm going to run make just to compile our code. That should run through. And we'll see what happens. This will be a good test that all the changes that we've made have worked, because this will give us exactly the same demo file that we saw previously. So it should look the same. So let's let that run through. Okay,
We run dot slash, oh, I don't type there. Here we go, dot slash QBRay. Now let's let that run, and let's just check what we get. Okay, so there we go. That is the test image that we've used before with the 5 balls on a plane. Now I know I've made comments about spheres on planes not being very exciting, and it's true, but this is the image we've worked with before, so it acts as a good demonstration. And we can immediately see that although this effect on the plane, the floor plane here, looks very cool, it is not what we had before. Now the reason for that is that we haven't specified the UV projection type, so it defaults based on the code that we've literally just looked at. It will default to the spherical projection, which means that it is applying a spherical UV projection to the plane, which results in this effect that we see here. So let's have a look at our code and just see how we can quickly change that to give the right effect. So where we make that change is in the scene file. So we go to scene.cpp, okay, and look down to where we define our object. So we have here, so we have floor. Here we're assigning the floor material to the floor object. Like so, but we're not specifying a UV type, which means that it will of course default to spherical. So what we're going to do is put floor m_UV map type equals QBRT : UV plane semicolon. Okay, so that's using the UV plane definition that we looked at just now from the object base class, and we're modifying the m_UV map type variable so that we should now get planar projection. So if we save that, let's go back to our terminal window, which is here. We're going to run make, just compile that. So that will just compile the modified scene file. That's a great thing about using make. We don't have to compile all of our files every time. If we run QBRay again, now hopefully let that run through, and we should, with a bit of luck, get back to the test image that we had before. And there we go. So, right, simply that modification, and we get back to what we had previously. Now we didn't need to make any change to the spheres, because obviously they're spheres. So using spherical UV mapping is going to work fine for those. But we did have to make a modification for the plane. Okay, so that's all well and good. What I want to look at is how did I go about creating the scene file for the image that we saw at the beginning. So let's have a look at that. Okay, so the first place to look is in capp.h, and what we do is we have a new scene file that I've created called scene_21 e21. So we're including that from here. Scene_e21.hpp we include, and we simply create an instance of the scene_e21 class called m_scene, and that will give us our new scene. So let's have a look what that scene file actually contains. Okay, so this is the CPP file for that. I'm not looking at the HPP file because it's exactly the same as the HPP file for the scene class that we've been using all along. Okay, so let's just have a look at what I've done specifically here. So for this particular scene, we of course initially configure our camera. We set the position, we set the look at, the up vector, we've talked about all that before. Update camera geometry, we set our ambient color to white, set our ambient light intensity to 1/4, and then we define the color maps that we need. We have a map for our wood, and we have our noise map, and we have our map for our fine texture. Okay, so I've just defined those as some nice shades of brown, and so on. Again, we talked about color maps in a previous video, so if you want to know more about that, go back and have a look at that. And now we set up the textures. So we have the spray can, if you remember, in the middle. So we load in the image texture for that, called qbspray1.bitmap. And we have the texture for the boxes, which is not a computational texture. So in that case, although we can do procedural wood textures with what we have, I couldn't with the code that's available in the public version of QBRay. There's no way to overlay different image maps, so I couldn't put the letters on top of a procedurally generated wood texture. That is something that we'll probably have in a future episode, and later on as a later feature to be added. A feature to be added later, that's what I'm trying to say. So for now we just bring that in. It's a texture that I created using other software, actually, Blender and GIMP and Inkscape. We can maybe do a future episode on making interesting textures to use with QB-Ray if that would be of interest. Anyway, we bring that in and we define our floor texture, which is a simple checker floor. We then have the textures for the wooden torus. Now this is the same multiple layer texture that I've used for the QB-Ray logo. So we create a wood pattern first using the marble texture, and then we create the dirt texture that just adds some rather subtle but significant anyway yellow blobs around the texture, and then we define a vertical gradient and a fine texture that adds the really fine detail to it. Okay. And then we create our normal maps. So we have the normal map for the wooden box. So the letters look embossed, or not embossed, what's the opposite of embossed? Indented, carved out, if you will. And that's done using a normal map from the file woodboxnormal.bitmap. And we define a texture normal for the wood as well, and a fine normal for the fine, and then a mirror normal as well, because we have the slightly rough reflections going on. So we use the simple rough normal map that we've talked about before. And then we create the materials for those. So we have the floor material, the spray body material. We define a metal material that we use for the conical part of the spray can, a white plastic material that we're using for the cap on the top, the mirror material that we're using for the mirrored walls at the back and at the left-hand side, which they have a normal map assigned to them from mirror norm. And this is an interesting point here, that if you want to create two versions of something, you can do this for textures as well, or materials as well as you can for objects. This is the syntax we use. So we want to create another version of mirror matte, but in a slightly different color. So we have the one on the left is yellow and the one on the back is blue. Rather than having to define everything again, we can actually make a copy of mirror matte and then just modify what we want. And the way we do that is with this method here. We make a shared pointer to an instance of type QBRT : simple material of a shared pointer to the object pointed to by mirror matte. Okay, so you star mirror matte to do that, and that will create a copy of mirror matte called mirror matte 2, and then we can simply modify the base color. Okay, so really easy way of saving time and a lot of effort when setting up more complicated scenes. We then define our box material, which simply is assigned the texture, box texture, and the normal map wood box normal that we mentioned just now. And then we have the wood material. This is the complex material that at the moment we're just applying to the donut. And that has the QB wood texture at the base, then the fine texture on top of that, and then the dirt texture, and then the vertical gradient. And it also has two normal maps applied as well. So the code that we have allows layering of textures and of normal maps, not currently of materials, but that's something we can look at later. And then we actually set up the objects themselves. The floor is simply a plane. The back wall is also simply a plane. Now we use the same method to copy back wall to make the side wall. Okay, so the same method that we use to make a copy of the material, we can use that technique to copy an object. And then we have to modify its transform and assign the different material to it. And then we define our spray can. Okay, so this is simply a cylinder and a cone and another cylinder for the top, and we assign the spray body material to the body using the cylindrical UV map type. Okay. And we simply have the metal mat to the cone and the white plastic material to the cylinder that represents the cap on the top. And that's how we go about making the spray can shape. Now, there's some limitations to doing it this way at the moment. We can't do composite shapes where you combine everything together. That will be the subject I'm thinking for the next episode. So that will be, I think, quite interesting. And then we define our box. So one simple box simply defined as an instance of box, and a type of material, assign the material box mat and set the UV map type to UV box. So that will use the box unfolding method that we've talked about. And then box 2, we simply make a copy of box with a different transformation matrix. Easy. And we define the torus as well. Worth noting, the torus comes from our ray marching implementation rather than a more classic ray tracing implementation of a torus. It's a bit slower, but I mean it does work, so we'll stick with that. And we set the radii and the transform matrix. We set the material to wood mat, and we set the UV map type to UV sphere. Now it will default to that, but I think it's quite nice just to do it explicitly. And then simply we push all of the objects back into mObjectList, and we set up our lights. We have 3 lights, one on the left, one on the right, and one at the top, set slightly back, slightly away from the camera, from the origin. And then that's it. Everything else then is just the code for rendering and so on. So that is the scene file that gives us the rather nice image that we saw at the beginning, and this will all be available on the GitHub repository, including the texture files and the normal maps as well, if you want to have a go at rendering this yourself. But for now, let's go to our terminal, let's compile this, and let's make sure it works. Okay, so let's run make again, let that run through. One thing to note, when you make modifications to capp.h, because it's a header file, make doesn't automatically pick up on those changes. So if you only change the header file, then you need to use make clean first to clean everything out, and you have to recompile everything. Again, there is a way of making gmake only clean out selected folders, which is quite powerful, but again, that's something we can look at later. So now that's done, let's run QBRay and let's have a look at what we get. Now this is quite a complex scene, so this does start to show the performance limitations of QBRay, which is something that I've mentioned before. Although it's effective and it makes good results, it is quite slow. It's worth bearing in mind we are running on the CPU, we're single threaded, we're not doing anything fancy, certainly no fancy GPU stuff. So there's quite a lot of scope for improving the performance of what we're doing. There's some quite actual basic changes that we could make, because there are improvements that could be made to the linear algebra library, which is my own. I put that together myself, and I'll do a dedicated episode on performance. Ray tracing. I mean, really the secret to making ray tracing go faster is reducing the number of ray object intersections. Every time you do a test for an intersection, that takes a long time, so you want to minimize the number of intersections that you have to test for, and that is really how you get performance. And if you do that properly, you can have a scene with millions of objects in it and still maintain reasonably good performance. But like I say, we'll look at that in a future episode. So I'm just trying to fill time while this renders, because I don't want to speed up the video, because I don't want to give a false impression of the performance. Someone did ask me if this ran in real time and what frame rate I got, and yeah, no, it doesn't run in real time. Not even close was the answer I gave to that, which I think was accurate. Nearly there. And there we go, yay! So this is the final scene. So like I say, all of the code required to generate the scene will be available in the GitHub repository if you want to have a look. And this really shows off all of the capabilities that QBRay has so far. And it's really starting to get quite sophisticated, although at the same time it is still really quite simple. So obviously, because we're not using path tracing or photon mapping that I talked about in the previous episode, we don't have any approximation of global illumination really beyond a basic ambient value, which is really not the same. And yeah, so it's simple, but it's effective. And as you can see, you can already start to get some really quite interesting and really quite sophisticated looking results. And to be honest, I'm really rather proud of it. Yeah. Okay, so there we go. That's really everything that I wanted to talk about today. We've gone over the topic of UV projection. We've talked about how it's different to basic UV mapping, and then we've looked at how we can implement it and how it's actually quite basic to implement, but we did have to make some quite substantial modifications to our code, or refactoring of our code, which obviously there's quite a lot to change there. And I didn't look at every individual file, but as I say, if you look in the GitHub repository, it will all be there. So that should be easy enough to see what's changed. And yes, well, there we go. I mean, I really hope that was of interest. I've had a great deal of pleasure making this video, especially making all of the animations, which are created with QBRay itself. It's worth noting. So yeah, I hope you found it interesting. If you like the video, please do remember to hit that like button. And if you haven't done so already, please consider subscribing to my channel so you don't have to miss any future videos. Thank you very much. Well, thank you very much for watching. It's been a pleasure, and I really look forward to seeing you in the next episode. Bye.